I'm going to give you some perspective here. So I've been spending the last couple of years re-engaging with the quantum community, talking with many physicists, and so I've sat in the physicist's shoes and had that perspective on say classical networking, and then now I'm on the other side. And so I hope that this perspective might be useful for folks here, and that we can bring these quantum and classical communication communities together. Ultimately, that's one of the things that I'd really like to see. And so I'm going to talk about these driving forces in systems research. What does it take to bring communication system or communications to a systems context and actual deployment from optical transmission to quantum optical transmission? So first off, an observation that is fairly obvious, but over more than a few meters, entanglement-assisted networks will be optical networks. And most commonly, fiber optic networks is what I think many of us anticipate. And so we have fiber optic networks, we have classical fiber optic networks, and this is what a classical fiber optic network would look like. So we have these things that we call ROADMs, reconfigurable optical add-drop multiplexers. They're actually switches that can select a given wavelength and then drop it down to some demultiplexer, or we can use it directly as a demultiplexer and connect it to different what we call wavelengths, which are different signals at different wavelengths of light. And typically in the C-band, where we operate over long distance, we might have 96 of these on a 50 gigahertz grid. These days, we have something called a flex grid, so we don't have to stay on that 50 gigahertz. We can move them all around. We can have different bandwidths for the channels and so forth. And these will go over a fiber link with amplifiers. And we have erbium doped fiber amplifiers, which are in line. And then we have Raman amplifiers that actually pump the fiber span. And because Raman is actually, the pumps are injected into the span. Anywhere that you have Raman, that's pretty much death to quantum signals. So bear that in mind when we're trying to put quantum and classical signals together. And many classical systems today use Raman amplification because of the good noise figure that you get out of it. Okay, so then, and yet we have a variety of different transceivers also that we support from 10 gig all the way up to 400 gig is sort of the latest thing. And we're trying to get to 800 and 1 terabit using advanced modulation format. So that's a DWDM transmission system. And just a few notes I want to say. So first off, in these systems, it doesn't matter when bits or photons arrive at the nodes, nor what polarization it is. Something a little bit different than some of these classical systems, right? So, and clocks are synchronized after demodulation at the endpoints, and data is only read at endpoints after full demodulation. We use amplified receivers, so we only care about the signal to noise ratio and not the losses or the power level. In fact, we maintain our power pretty much at what we call a constant launch power throughout the system. And we have control loops in these systems that maintain optimum launch power into the fiber spans for each channel and maintain constant gain on the amplifiers. Those are the main control loops that we use. And bits flow continuously. They're not bursty like packets or anything like that. Even if you're not sending any data, we'll be sending dummy bits over the line to basically stabilize the system and make sure that it doesn't start misbehaving. We use optical switches, but only to configure the system, not to actually switch bits. All right. So, and these operate on minutes or hour timescales, not on nanosecond timescales and things like that. And there's very good reasons why all these things are, why we don't deal with polarization and timing, and we don't switch in these networks. And it's because that's what we had to do to make these networks work. All right. So how did these systems develop? So a lot of people talk about ARPANET and NSFNet, and these were built over the existing telephony network. But about 20 years after that, the fiber networks came along. Okay, so that's in the 1990s. It wasn't until the 1990s that fiber networks came along. And I would argue that in looking at classical networks and trying to understand how they developed and think about how that might relate to the quantum network, I would say that, or quantum internet, I would say that we should look towards the fiber optic networks and how they were developed, because I think there's a lot more analogy and connection with or commonality with the development of fiber networks with quantum than say packet networks and so forth. So and here's an interesting quote. So there in a very early day, so like 1990 basically, there was an effort to build test beds around the US. And they had this, what they call the Gigabit test beds, and there's multiple test beds at different locations. They didn't have optical amplifiers at the time. Kind of like we don't have quantum repeaters right now, right? So they could only do a sort of local networks, the short reach networks, whatever the fiber loss would allow. Or they had to do an actual repeater where you drop the signal completely, receive it, and then retransmit it that way, like our trusted nodes, let's say. And there's an interesting quote in there. So prior to the time the test beds were being formed in 1990, very little hands-on research in gigabit networking was taking place. There was a good deal of interest in high-speed networking within the research community, consisting mostly of paper studies and simulations, along with laboratory work at the device level. So exactly the way we are today, right? People were working with things, with devices in the lab. I was a graduate student at the time and working in physics and studying lasers and all optical regenerators and all sorts of nonlinear optical devices. And it seemed obvious to me, wow, why can't we just make a long haul fiber optic network? This is going to be easy. And the reality is that there's all sorts of complications there. And well, one of the things that happened during that period from 1990 to 96, well, I should say shortly before that, the erbium doped fiber amplifier was invented in 1987. Invented, and that's a big tabletop experiment, not something with semiconductor lasers that you could actually use in a system. So there was no commercial erbium doped fiber amplifiers or something that you could use in a system until sort of into the 1990s, so several years later. And while those test beds were running, so they were able to come up with a viable amplifier. And so then they started doing long distance experiments. And that was really the birth of system engineering and communication systems for optical systems. And this is a very famous paper from Bergano and Davidson. So Neil Bergano and his guys, they were working on submarine systems, so trying to send them underneath the ocean and very long distances. And it's very expensive to have many amplifiers. And of course, you can use a spool of fiber to get your distance. But if you have to do 20 of them, right, it starts to add up. And so what they came up with was a way to emulate that very long distance transmission by creating a loop where they could actually feed the bits from a transmitter into this loop with a coupler. And they have a couple of switches, and they would close the loading switch and load bits into this loop, and then basically close the loop switch and open the loading switch. And they let those bits just circulate inside the loop. And you can accumulate distance that way. And this sort of recirculating loop innovation really changed the game for long distance fiber optic transmission system engineering. And very quickly, so this is some results from that paper where they were able to show transmission out to 9,000 kilometers, 20,000 kilometers. But the key thing is that this was something where you could do it in a single lab. It was affordable. You just needed 4 or 5 amplifiers, maybe 6 amplifiers, some spools of fiber. And you can really play with this in terms of you can vary, you can vary the distance, and you can change the modulation format. So you can put different transceivers in there. You can change the power levels that you're using. We had to deal with dispersion at the time, so you have different dispersion management strategies. Basically, you could experiment with all of these different system parameters in this environment. And another key thing about this was the metric that you used was the bit error rate at the receiver. And all that you cared about is, how do I get all of my channels above some threshold bit error rate? And if it's good, I got it. I have my hero experiment. I check it off. I publish it. I got a post-deadline paper at OFC. And that simplicity of how you can achieve a certain result and having that as kind of a common baseline that everyone is working towards and common methods really enabled this technique to be widely used. And I just threw in a few examples. So Greg Raybon threw in an all-optical regenerator into one of these loops. And then he showed that you could basically keep the transmission going forever and still be error-free. And so that was this result in 2002. I'll look forward to the time when we have quantum repeaters and we can show this experiment for a quantum signal, right? Here's an example where this was something that I put together. When I was working in this space, people were starting to do mesh networking, and they worried about sending signals on path diversity on different paths of different distances. And so we broke up signals into different groups using a set of switches inside the loop. So we could have essentially 8 different loops from 8 different groups of channels in one, where the signals are all going different distances. And so that was one crazy variant of the recirculating loop. Here's a recent one on space division multiplexing, where they actually, so this is multi-mode fiber basically, and you need a multi-mode amplifier. So they have all sorts of fancy tools and amplifiers and things that they're putting in this recirculating loop here. But again, it's still a recirculating loop experiment, and so everyone understands it, and they're able to innovate around that. And ultimately, there was this kind of system capacity race that took place starting from the early 1990s when Bergano first came up with this idea, and then over many decades, well, a couple decades, but many decades of capacity improvement resulted from all of these experiments, one hero experiment after another every year. And going. And so, but I want to point out, so that's the system research, classical transmission system research activity. That's not how you engineer classical systems. In a classical system, I don't just look at my bit error rate and try and get some bit error rate. I actually have to deal with a metric that we call the quality of transmission metric, or the QOT. And then also I'll apply certain margins to my transmission performance. So the curves here I'm showing, Q factor is like a signal to noise ratio. And if you vary the launch power of the signals going into the fiber at low power, you're limited by the amplifier noise. So your signal to noise ratio is poor. You're down on the left-hand side here. At high power, your signal to noise ratio goes down again because nonlinear effects kick in. So you get this kind of optimum region. And you're always looking for that optimum launch power, and you want to stay in there. But there's some uncertainty about what power you can achieve. So you have a range of power that you have to tolerate. And then you set some margin. So the forward error correction is usually where your threshold is. For all these hero experiments, that's what you use. But in practice, you can never use that. You can't run a system right at the limit. So you have this engineering margin that you apply above that. And basically, above the margin, you say that the signal's okay, and below the margin, you don't allow the signal to be set up because it's going to have poor performance. And you perform an estimation even before you establish a signal. So you try to estimate what this QOT is, and then you route your signal through the network, and you see how well you did, and make sure it's within the margins. This is how you engineer an optical system. It's not how you do research on an optical system. It's not how system engineering research is done. The recirculating loop experiments that I talked about is how the system experiments are done. So, so quantum internet is like building the fiber optic internet in the late 80s and 90s. And there's plenty of device research in labs, theory, but no systems yet. So we need to develop this type of systems research practice. And I want to point to another interesting it's kind of testbed experiment that happened, the Monet Project. This is a very famous project that many people credit or say it was one of the things that led to the explosion of the bubble, the telecom bubble that happened, right? And basically, if you look at the figure here from Rich Wagner's paper on it, so you have some sort of mesh network in here. You have what looks like one of these, what I call the ROTM, an add-drop multiplexer with the different amplifiers. And it's starting to look like systems that we have today and using a lot of advanced technologies. And what happened out of this is that people realized that you could really develop these optical transmission systems and make very dense, highly complex, and even switched optical transmission systems, and it was a viable sort of product path to go after. And so numerous startup companies emerged from the people working on this from this particular project, right? And one of the reasons I want to highlight this is that basically that's what the test bed was. But this figure here kind of shows what they built. And this is a figure from the Lucent Wavestar 10G system. And it's basically just some transceivers, and there's dispersion compensating modules in there and amplifiers. And you're going over 1, 2, 3 spans in this particular configuration. Actually, I think they could go up to maybe 6 spans of fiber. So although they had this very fancy switched network that was quite flexible and tunable in that testbed experiment, what came out of that in terms of commercial systems that actually got built were small point-to-point systems with a few fiber spans, and actually this whole system here had to be manually designed and configured for each deployment that you put out there. And so it's a much simpler version of that. And there were a bunch of technologies that got dropped from that Monet experience. So they used acousto-optic tunable filters. Those got completely dropped. They're nowhere in sight. We don't deal with those. Coherent transceivers, okay, they got dropped, but 20 years later, the technology caught up to them, and then we're using them today. Wavelength cross connects and add drop multiplexers, again, they didn't make it into product right away, but 10 years later, they started to be used in products. Tunable transceivers took 10 years before they made it into product at that point. Mesh networking took another 15 years before they were actually used in products. And space division multiplexing is another one that sort of a complex technology. I showed you that recirculating loop on it, but it's so complex that there's a simpler solution of using parallel fibers, and people are moving to that. Maybe 10, 20 years from now, it'll actually find its way into product, I don't know. So for physics research, going over to systems, so many of the core technologies were investigated for 20 plus years, lasers, fibers, MEMS, these switches and so forth. And but what we saw was that new technologies, when there was a real need for the functionality of those new technologies, it's basically 2 years until you get into that system experiment, and 5 years to product. And so the erbium doped fiber amplifier was an example of that. It went to product very quickly. Pump lasers for Raman amplifiers and erbium doped fiber amplifiers. Actually, fiber connectors, wavelength switches, all sort of followed this kind of path. Now I want to just briefly, how much time I have here, talk about, say, quantum systems and think about them in the context of what I just went through. So here's an example of a kind of repeater system that Saikat Guha and his team put together. I'll pick on Saikat a little bit here. So first off, we ask, what's the metric that will drive engineering innovation? When I look at a layout like this, I'm not seeing where my metric is. So we can talk about the E bit rate, right? And maybe an E bit rate distance product could be an interesting metric. How do I build one of these in a lab and start to try to push that E bit rate and distance product? And what are the problems and impairments to overcome? Maybe the source generation rate, the switching and heralding speed, the timing and polarization drift. And there's an important thing that's often missing in these types of system figures, right? So in general, there's going to be this classical network that is tightly connected and integrated with that whole quantum repeater network. And it has to do polarization control after these signals go across transmission, time of flight signal alignment, precise time synchronization across the network, high-speed optical switching, fault localization. And these are all things that we can do in labs today. They seem easy enough. But if you told me that you wanted to build a communication network where you had to control the polarization throughout the network, I would say forget it. That's never going to make it into product. Okay, if you have to synchronize the timing throughout the network, these are very challenging problems. And there have been many examples in the classical world where people came up with schemes where they wanted to do something like this, and it always fell flat because it was just too complex to manage it in a product environment. And if the problems are too complex and too interconnected, then they're difficult to innovate on. How do I innovate and be able to have that evolutionary path where I can improve performance over and over again, which I think is so critical when we get into a systems and engineering environment. So the development of fiber optic internet is, I think, a good historical model for us to look at with eyes wide open about the challenges that we're facing in building these entanglement assisted communication networks and a quantum internet. So, and I really want to emphasize that test beds are key to growing system engineering research community and methods. And even if the test bed is so far ahead and so far out there, what you see is that that kind of test bed and the results that come out of it can drive the innovation where the commercial systems and what makes it into product follows behind what was in those test beds. But if you're not showing what can be done in the future and what the potential is, you're not getting the progress on the backside from the commercial systems. And these system experiments really should reach far ahead and then create a pathway to innovation. And we need to find the metrics and methods that will lead to these high growth engineering cycles. I mean, the beautiful example that we are familiar with is in quantum computers, increasing the number of qubits inside these quantum computers. It's simple, clear, you understand what needs to be done. There's opportunities to innovate around that and achieve that. So we need a similar thing for communication systems as we think about these repeater type networks and so forth. And I can't emphasize enough, if it's too complex, then it's not going to go anywhere. Okay, and that's my talk. Thanks.
All right. So Dan, thank you so much. This was really great overview and connection to of the where we are right now with quantum and where we were in the past. I was not participating in the telecom research. When it started to happen, I was actually on the other side, the financial side. I was buying and selling telecom stocks for Goldman Sachs. So this was a very interesting perspective. Now, the organizer prepared a few questions to get the discussion started. So let me ask you those, and then we'll take questions from the audience. Since this is a loaded question, I think that's the first question that gets asked whenever you bring up quantum, and it is, you've described a path forward towards kind of systems level research on quantum networks. What do you think will be the main use case for them, in your opinion? That's question one. And you want to address that first?
Yeah. So I firmly believe that, I mean, just look at what the big web scale guys are doing, right? They're building quantum computers so they can accelerate AI and solving certain problems more rapidly. Even getting a little bit faster with your AI algorithms means money for these companies, right? And if you look at many of the startups out there, they're just a little step behind. And we're seeing tabletop quantum computers, something that could fit in my office, that these companies are developing. And so I think, when I was a grad student, there were these, we had these workstations, like there was the HP workstation that everyone was trying to get to do their simulations and so forth. So I see in the near future, we're going to have at universities, companies, anyone who's working on chemistry simulation, physical simulation modeling, AI type algorithm development, they're going to want to buy one of these tabletop systems, but it's still going to be limited in the number of qubits that it has. And the web scale folks are going to be offering cloud quantum computing And so the key is that I'll want to basically be able to entangle my local quantum computer with the cloud when I need that extra power. And I see that as a huge driver. I mean, that's going to be a game changer for what we can all do in terms of computing in businesses and universities. Yeah.
Thank you. This very, very informative answer. So on the path of realizing this, besides obvious systems level research questions that you've identified, what kind of challenges do you see?
Well, so I mean, most of what I talked about in my talk was the challenges, I guess, but I don't want to say that I'm pessimistic about it, and my talk was not intended to discourage people, but that we should be aware of these challenges. And while we're going to do things with quantum networks that we never got working with classical networks, like polarization control and things like that. And it just wasn't that as important in classical networks. And there's examples. I look at the Raman amplifier, okay? I was at Lucent at the time when they developed a commercial Raman amplifier. No one had it. And that was a really hard effort, and they solved so many practical problems. And that's the reason we all have Raman amplifiers today. It was hundreds of millions of dollars invested in that. But they did it. They made it work. Right. And I think you can do similar things solving difficult problems. But we have to pick those problems, find the right ones to solve that are going to enable some key functionality that we need in these systems. And basically, again, put us on that. There has to be some sort of path that we're going to be able to start with this low performance, barely making it work kind of system. And then over time, improve it, and it'll get better. The bit rates will go up, the distances will increase, and we'll move forward. Yeah.
I completely agree with you on this. It's It's now last question, and it's actually I think you've more or less answered it in your first answer. Is what possibility do you see for quantum technology to contribute to success of the 6G networks, whatever they will be in the future? And I think that you've answered in terms of enabling the entanglement between these tabletop quantum computers in, say, a lab or.
But I don't know that you're going to be doing that in 6G, right? So the interesting question is what's going to happen with security, right? And post-quantum security, I mean, there's this, I'm one who believes that it's not as simple as saying that there'll be no QKD or everyone's going to be using QKD. I think we're going to find applications for quantum techniques in security systems going forward, but it's not going to be what we thought originally. And how it's going to be used, it's going to be used synergistically with classical techniques. So that'll be really interesting to see how that develops. And I think that needs to be integrated with 6G and will be a part of the radio systems right out to the cell tower. And there are ways to do fairly low cost integrated devices, maybe that are doing a few photon signals that then go back to a more complex single photon counting system somewhere else, right? That would be more expensive. So we'll be finding solutions like that so that we can get some sort of quantum functionality out to the cell tower or the access point. Yeah.
Yeah, I do agree with you that the security, the RSA security, and even the even the very weak just computation-based algorithms that are still being used in some places are not going away anywhere. And I think that augmenting them with quantum enabled effects as necessary is the way to go. So yeah. Now, does the audience have questions? Press your button.